Hello, this is Xiang Li from Stony Brook University, and today I'm glad to share our recent observations on this question. Does self-supervised learning really improve reinforcement learning from pixels? Well, the very short answer to this question is, unfortunately, no. And to be more precise, our observations suggest that the existing self-supervised learning framework for reinforcement learning fails to bring meaningful improvements over the baselines when the same amount of data and argumentation is used. Previous works regard self-supervised learning loss as an auxiliary loss and apply both self-supervised learning and reinforcement learning losses alternately during training. For example, this method combines self-edited credit with autoencoder, and this COIL combines self-edited credit with MOCO, which is a famous contrastive learning method. Again, both of them jointly optimize two losses for each batch of data, and we apply two losses alternately. In this paper, we extend this learning framework to a general joint learning framework and run an extensive amount of experiments to figure out which self-supervised loss benefits reinforcement learning most. For each batch of samples, we first apply image augmentation to all the samples and use augmented images to perform reinforcement learning updates. After that, we use the same augmented data to perform self-supervised learning updates. With this framework, we can easily compare all the self-supervised learning losses fairly. We tested 19 self-supervised learning losses in 4 categories, including 9 context prediction tasks that are specifically designed for reinforcement learning. And we first test how well these losses perform when they are applied solely. Then, we also investigate the combination of multiple losses, and we use evolutionary research to find the optimal loss combination, as well as the magnitude of image augmentation, which is also a very important factor we found in our ablation. Finally, we benchmark all the methods on various environments with multiple random Cs. Here come the results. We use a relatively performance score over 6 environments from DeepMind Control Suite to compare all these methods. The red bar stands for the vanilla self-edited credit without any augmentation or self-supervised learning. The blue methods only take advantage of image augmentation without any self-supervised learning. The green methods have only one self-supervised loss applied with image augmentation. The orange methods are manually designed to combine two self-supervised losses with augmentation. And finally, the green methods are evolving losses, which automatically combine multiple self-supervised losses and the magnitude of image augmentation. From this figure, we find that image augmentation plays a very important role in visual reinforcement learning, since the performance of vanilla self-edited credit is significantly lower than others. However, some self-supervised losses can even ruin the advantages brought by image augmentation and perform worse than the baseline. Finally, all the self-supervised learning methods fail to outperform DRQ, which is purely based on image augmentation. As for Atari benchmark, most of the self-supervised learning methods also failed to bring meaningful improvement. Rainbow with autoencoder was the best approach that outperformed other baselines, but note that this method didn't perform well in DeepMind Control Suite. In our robot experiments, the goal is to move the robot arm close to the target as fast as possible. Again, we confirm that image augmentation is important, while the role of self-supervised learning is usually limited. To conclude, our extensive experiments suggest that the role of self-supervised learning with the existing joint learning framework is usually limited, while the selection of image augmentation is more important. Again, we confirm that there is no golden self-supervised learning or image augmentation method that works for all the environments, and one should cautiously decide the design choice of image augmentation or self-supervised learning for a specific reinforcement learning task. We also have detailed ablations, representation analysis, and other training frameworks presented in the appendix, and our code for evolving losses is available at the link here. We hope this work inspires future works that introduce more losses designed specifically for reinforcement learning, as well as new training frameworks. Thank you for your attention.